Okay, recording is activated. So just to make a summary of what I would like to do now, I would appreciate if you could open RStudio and you get to this opening screen. Just let me check if, yeah. Can you see my screen with RStudio now? Can you please confirm?
Yes.
Okay, very good. Because for some reason on the phone I can't see it, so I think I need to wait a little bit. Okay, very good. Now, what is the exercise that I would like to propose to you now? Again, if you have any problem in opening RStudio, just let me know, because if we can resolve it, I would appreciate very much. Let me shift this window on the other screen so I can see the chat in real time. Very good. Now, yeah, yes, please.
What is the command to clear the history in RStudio?
I think what I did, it's just to switch the upper right window on connection, because there is to clean the history. I mean, I don't know if there is a possibility to clean it, and we should check. It is a good question. Let's make a check. So let me just write here, Arbor in Google. I open a Google window, google.com. Okay, very good. And then I look for R project and clear history. Let's see if there is a command. Clear history shortcut. Okay. Let's see. Okay, there is a broom here. Let's see. Okay, this one. You see where my mouse is pointing? Clear all history entries. Can you see it?
Okay, yes, thank you.
Yeah, but I prefer to keep it in my case, because this history is the exercise that I would like to propose to you. So in case there is something that I don't remember, I prefer to keep it. Give me just 1 second, because I still can't see on the phone and I don't understand why. Let me leave the meeting and try to leave the meeting with the phone and try to, let me see, because I don't understand. Let me just check. Okay, I think I can make this. Let me check 1 second, because otherwise. Okay. So, what is the exercise that I would like to propose to you to continue our training? First of all, let me clear the console in RStudio, Control L. And at this stage, let me go back to our lectures in order to get an exercise for training that in a way is related to what we are discussing. So I go to our tutorials. Here we are. And then let's go to forcing estimation for Arbor design. And you may remember that we discussed this lecture and we got to the estimation of the wind forcing. Now, what I would like to recall back is the definition of probability. So we, as you may remember, we just made a brief recap of what probability is. And when I made a pool among you, some of you said that it was not needed. Some others said that it was needed indeed. Now, let me just integrate the recap that I did with an exercise. I think it is useful because with this exercise, we get 2 opportunities. The first opportunity is to make sure that we really understand what probability is, and in particular, to make sure that we really understand what is the difference between cumulative probability and probability density. And the second opportunity is that we can practice in R. So you will see that the exercise looks trivial, but actually getting it done in R, it's not easy. So what I would like to do, what I would like to do is to estimate the probability density for a series of numbers. And the probability density, the equation is this one, okay? And just keep into account that what we have to do is to estimate for a series of numbers. We have a series of numbers. You will see what the series is about. And we have to split the domain of these numbers in discrete intervals. And we have to count the number of times that each number falls in each interval. Okay, so what we have to do, let me take the graphic blackboard. I want to make a scheme so it's perfectly clear what we have to do. And applications, just 1 second that I get the graphic blackboard turned on. Here we are, and let me make it file new. Okay. Okay. Give me 1 second because I need to put it on the screen. So let me, okay, here we are. And then let me make it a little bit, here we are, okay. Perfect, and here. But yeah, because I need the blackboard otherwise. Okay, I am almost ready. Let me share the right screen, and I am actually ready. Okay. I need to share screen number 2. Good. And then let me go to the blackboard. Okay. You should see my blackboard now, and let me just change the color and let me draw a straight line. Okay, good. So let's suppose that we have a series of numbers which is defined over a given domain. This is the domain of my numbers. Let's suppose that the domain is between -4 and 4. Okay, this is 4, and this is 0. Now, what I have to do is to split the domain in discrete intervals. So it may be like this. Okay. Okay, perfect. And for each interval, I have to compute the number of observations that are inside each interval. And the total number of observation is n. N is sample size. Sample size is the terminology that we use to identify the number of observations that we have. So we have to compute the number of times each observation falls, observations fall in each interval, okay? And if this number is ni, I can compute the frequency, fi, which is equal to, it's equal to ni divided by n. Okay, and let's suppose that the intervals have dimension delta x. Okay, perfect. Now, what I have to do in order to compute the probability density f x, what I have to do is to compute, it is given the probability density, remember, by the limit for delta x tending to 0 and n tending to infinity of what? Of the frequency fi divided by delta x. This is basically the formula that you find on on the lectures on my website, if you look at the formula, actually it's a little bit different because the symbols are different. And in particular, you see that the interval has an amplitude of 2 delta x, but it doesn't make any difference. When you bring delta x close to 0, the fact that the interval, the amplitude is given by delta x or 2 delta x, it doesn't make any difference. It's just a matter of convention. And basically, we have to find the limit for delta x tending to 0 and n tending to infinity of the frequency of the observations falling in each interval divided by the amplitude of the interval. So if you go here, it's the same formula. Limit delta x tending to 0 and n tending to infinity of the frequency in each interval divided by delta x. So this is what we have to do. So we get a series of numbers. We get to count the number of times that observations fall in each interval, ni, and then we get to compute the frequency, and then we compute for each interval the frequency divided by delta x. Of course, when we do it in practice, we have to fix a delta x, so we cannot bring it to 0. So we have to take a delta x that is sufficiently small, and also n cannot be infinity, so we have to take a large n. Okay, so let's try to make this exercise with R, because it's very easy to do. On the other hand, it requires some programming skills. First of all, let's generate the series of numbers. R has many functions to generate random numbers. We could take something that was really observed, but to make it quicker, let me just generate it. And let's call it like something like PR1. It's your choice, the name of the variable. PR1, what is PR1? It's the vector of the observations. And let's generate it with this function, rnorm. And you just have to put the number of observation that you want to generate between parentheses. So I put 1000. 1000, it's not infinity, but it's quite large. I think you cannot see RStudio. Just 1 second, because I need to change the sharing on the screen number 2. Just 1 second. Good. Now, in a moment, you should see it. Perfect. So you see the instruction that I used. PR1 equal rnorm 1000. Please get it. Okay, and you may wonder, what is this function rnorm? It's a function to simulate, as I said, random numbers. Actually, this function generates random numbers that follow the normal distribution. But you could use any other generator. The program the code that I'm writing, the exercise that I'm doing, you can apply it to any series of numbers. Okay. Now, let's see what is the range of these numbers, min PR1. And while I make this exercise, please take note of the functions. Min gives to you the minimum value of a vector. And in the same way, we can write max. You see that the minimum is minus 3.17 something, and the max is 3.37 something. It is, as you can see, it is roughly symmetric around 0. This is what we expected, because the normal distribution is symmetric around the mean, around the average. And the function rnorm that I used in this way indeed generates random numbers according to the normal distribution with mean 0 and standard deviation 1, but don't bother about the details, okay? If you don't understand what standard deviation is, let's forget it. What I just want you to get from here is the range, okay? So our numbers are varying from minus 3.17 and the max is 3.37. What is the average? Let's compute the average. Mean PR1. It's around 0. Remember, the purpose of this exercise is also to train on R. And therefore, any function that I use, if you don't know it, I suggest that you take a note on a sheet like computing the average. The function is mean, function minimum, function maximum. Take note, okay? So this is our, as I said, our mean. We may want to make a plot PR1. You see the plot. It's random numbers, so you shouldn't be concerned by the scatter. And if you want a line, plot type equal line. If I am too fast, please step in. Write on the chat, let me know if you want some clarification, questions. I think it is important that you can follow me. Okay, good. So this is what we know, the range. Now we have to do what I depicted into the graphic blackboard. Let me show you. I have to split the range into discrete intervals. Look at that. I knew that the range was more or less varying from -4 to 4. And therefore, let's take this safety range from -4 to 4. It's a larger range with respect to the range of our numbers, but it's no problem. If it's larger, it's no problem. It means that in some discrete intervals, we will get 0 numbers falling into that, but it's not a problem. So let's split the range from -4 to 4 in intervals with a width, an amplitude of 0.1. It means 80 intervals. Okay, so the number of intervals which I am using to discretize the range from -4 to 4, the number of intervals is 80 because I want a width of the intervals. I want a delta x of 0.1. Okay, let's remove the graphic blackboard and then let's make this split. However, let me try to make the split. Let me try to put together the splitting and the counting. And to do that, you know, I have to make the same operation 80 times. I have to identify an interval, which may be, for instance, from -4 to -3.9. This is the first interval. So I have to define it and count the number of observations falling into the interval. This is something that I have to repeat 80 times. It happens frequently in computer programming that you have to repeat the same operation for many times. And actually, this is when programming is really useful. I mean, if you have to repeat several operations several times, this is when programming becomes useful. It is especially useful programming, making a code, if you have to repeat the same task several times. Okay, so what is the tool in computer programming that we use to repeat an operation several times? It's a cycle. We call it a cycle. And any programming language has two basic structures which allow you to make programs. They are cycles and conditions. Let's forget about conditions for now. We focus on cycles, okay? So what we have to learn is for any given language, what is the instruction that you may use to build a cycle? Let me check the chat because I want to make sure that I'm not losing anyone. Perfect. No messages. So what is the instruction that in R, to be more specific, I need to use to build a cycle? This instruction, look at the R Studio console, is for. You see that when I indeed type 4, the help of R Studio gives to me some suggestions, and the first one is precisely 4. Okay, now For is a function. Let's give the argument. And first of all, I need to put a counter because I have to tell the program how many times the cycle is to be repeated. And I use a counter. I define a counter to specify how many times I want the for cycle to be repeated. So for I, this is my counter. You can put whatever name there. You can put A, B, C, whatever. And I put I because I like this variable for a counter, a cycle counter. And then I have to give the range in 180. So this instruction, take a note or keep it in your history. It's the instruction that I use to tell R, repeat the following operations, the following tasks, which I will need to specify. Repeat the following tasks 80 times by using the variable I as a counter. Okay, if I push return now, you see that R puts a plus there. The plus is a question. R is asking me what are the tasks to be repeated. Good. Now, if you have several tasks, you need to put a curly bracket. You need to open a curly bracket. If you have only one task, you can avoid the curly bracket. But with several tasks, like I am doing now, I need to put a curly bracket, okay? And the curly bracket, how to obtain it with my keyboard, and I suggest that you try this key combination. With my keyboard, I press Alt-GR. It's on the right of the space bar. There is the key Alt-GR. You should press it, keep it pressed, and then press the key of the number 7. Okay. You see that again, I redo it. Alt-GR number 7. They have to be pressed together. And in my case, I got the two curly brackets. If you have a US keyboard, you have a key with the curly bracket that you can press directly. Okay. If you have any problem in getting the curly bracket, let me know on the chat. Okay. Now you see that when I put the opening, the left bracket, automatically RStudio puts the right bracket. Okay. Now, if I now press enter, nothing is done because there was no instruction to execute. Okay. But we learned how to make a for cycle. Let me make another example of a for cycle. Very simple one. Let me clear the screen. I go with the arrow up and I get back for I in 180. And let me put just in 1.4 because 80 is too much. Now let's give only one instruction. I can do without the curly brackets, and the instruction is write on the screen something. Okay, so let me write cut. Cut is the function to write on the screen. And I can do cut the variable I, comma, and add something more. I'm not sure whether, no, let's put only cut I, but let's tell him to put a, to go to a new line every time it's the task is executed. You see, this is another example of a very simple for cycle. And you learned the name of the function to print on the screen. Again, the argument fill equal true. It means take a new line. Now let me repeat it. I go with the arrow up for I in 1.4. Let's try to remove the fill to see what happens. You see what's going to happen because I didn't put the new line. Okay, now let's go back to our exercise. Okay. so let me clear the screen. Before I start, let me define a variable PR2, a vector 0, and another one PR3 0, because I need to use these vectors inside the for cycle. And when you assign values to a vector, you need to have the vector defined in advance. You may say that I define two variables, not two vectors, but the way to define a vector in R, it's a simplified way, is to define it as a variable, and then when you assign values, more than one value to the variable, it automatically takes it as a vector. Okay, so let's define these two variables, which later on will become vectors, because I need it. Okay, and now let me go back with the arrow up to the instruction of the for cycle 80 times. Good. Now curly brackets. Oops, sorry, this was not the curly but the square. And let me cancel the right bracket and I go to a new line. You see that it's still waiting. Okay, waiting for instruction. Perfect. Now let me compute the frequency. Okay, and remember that the vector of the observation is called PR1. Okay, now let me compute the frequencies, or the number of times that numbers fall in each interval. So let me put the number of times in a vector which I previously defined called PR2. So PR2 is equal to length. Length means the length of a vector of what? PR1. And then I put conditions. If I just, and first of all, let me write here, not PR2, but PR2I, because I need to count the observations falling in each interval. So I need to create a vector. And then I give the index I to each vector element. So in each step of the for cycle, it goes from the first interval to the second interval, the third interval, and makes the count, okay? This is when I would get an error if I hadn't defined in advance PR2. If I make an assignment, like the one that you see on the screen, the last one, without previously defining PR2, I would get an error. Okay. Now, what is the content of each element of PR2? Again, it's the number of times in PR1 observations fall in each interval. How can I count them? Through the instruction length that I should apply to PR1, but I need to give a condition. So it shouldn't compute the length, just the length of PR1. This is 1000, I already know it. It should compute the length of PR1 within each interval. So let me give the condition. And the condition is such that condition is to be given between square parentheses. Okay, square parentheses, you have on the keyboard how to get them. And so I don't think there is the need to tell you. And the condition is such that PR1 is greater than what? Greater than, remember, we start from -4. So greater than, let me open a parenthesis, -4 plus E-1 times 0.1. This is my condition. My condition basically says that PR1 must be greater of what? -4 plus E-1 times 0.1. So at the first step of the cycle, E is 1. So this condition, E-1 is 0, simply says that PR1 must be greater than -4. At the second step, E will be equal to 2. So the condition will say that PR1 must be greater than 3.9. Perfect. Now I have to put another condition. It's not finished because this is the first condition, but I have to put another one because PR1 must also be lower than what? Let me open the parentheses. It's -4 plus E times 0.1. And this is the second condition. Okay, I'm now missing, I need to put the, I don't remember if the square parenthesis is to be put here or there. Let's see, we can try, okay? I think the condition should be given, both of them, within the same square parenthesis, but we can try. And this is counting in the first, again, in the first step of the cycle, E is 1. So it's counting the length of PR1 under two conditions. PR1 must be greater than -4 and PR1 must be lower than -3.9. Will it work? We will see. The second,
Professor?
yeah, please.
I think that -4, the second condition should be -4 plus I times 0.1.
Yeah, correct. Thank you. This is very good. It means that you are following me. Thanks a lot. Okay, and then let me just define another task. The other task is let me compute PR3, and with PR3 I need, let me compute the left boundary of each interval, because at the end of the story I need to put the probability, to plot the probability density against the interval, against -4, -3.9. So let me compute it. PR3 is equal to -4, sorry. And let me put a parenthesis here because so it's clearer. Is equal to -4 plus E -1 times 0.1. And I think here I have to put another round parenthesis. Okay, this is the abscissa of the graph that I will plot. So at this stage, I can close the curly bracket and let's try to see if it works. And how can I close the curly bracket? The right curly bracket is Alt-GR plus 0, the number 0. So you may remember that I had a doubt whether the square parenthesis, the right square parenthesis is placed in the right position. Let's see if it works. Okay, it seems yes. Now let's look at what we got. The easiest is PR3. I forgot one thing. PR3, I forgot the index I. So I need to repeat everything. It's not a big problem because I can go back with the arrow up. So let me repeat it, okay? 1, 2, 3, 4, 5, 6. Okay, this is the first instruction of the 4. 1, 2, 3, 4, 5, 6. This is the one that I need to correct. And I put the I here. Good. Now let me make a check. PR3. Very good. From -4 to 3.9. And this is the sequence of the left boundary of each interval. Let me see PR2. Very good. You see the counting. Actually, PR2 should sum up to something like 1,000. Let me check it. Sum PR2, it's 1,000. Perfect. Everything is clear? Okay, but now if everything is clear, we are ready to plot the probability density. Let me clear the screen and let me write plot. What do we need to plot? First of all, let's forget about plot for now. I have the sequence PR3 of the left boundaries of the intervals. Let's plot the probability density with respect not to the left boundary, but to the center of the interval. So what I have to do is PR3 is equal to PR3 plus 0.05. Now let me see PR3. Very good. Now we got the center of the interval. Okay, perfect. Now let me make the plot. So the abscissa is PR3. And the ordinates are PR2, but I have to divide PR2 by 1000 because it's frequency divided by 0.1, which is the length of the interval, delta x. And let me put type equal line. So let's see what happens here. Perfect. This is my probability density. You know that it's a bit up and down. It's a bit. It's not smooth. But why it is not smooth? Because we used a length of the interval that is too small for the given sample size. So what we could do, if we want to get a graph that is smoother, is to increase the sample size. So let me try to indeed remake it by increasing the sample size. It's not a problem because I just have to look at my history. So let me look at the history here.
Excuse me, Professor.
Yeah.
I'm not getting the same results as you. Could you just repeat the last few parts?
Yes, this is perfect. And so let me just go to the history. I think this is. So do you think I need to repeat the fourth cycle? Because if you wanna repeat, let's look at our history. This is the last fourth cycle that I did, and now if you wanna repeat it, you select the history in this way, and I push on to console. Look at the console. This is a way to repeat the history. And then what I did is to get this one and the plot. Oh, sorry, let me see if I can. Yeah, in this way, you see, I can put to console these two instructions, and what I get is again the graph. This is what I did. You can see on the console. And remember one thing, that you have a different series of random numbers. So the graph may look a little bit different. I'm not sure whether you got what I said, but what I can suggest to you is to repeat with me the exercise with a longer sample size. So let me clear the console. And let's go back to the history, to the definition of PR1. Here it is. Let's put it to console. But instead of 1000, let's put 1 million. Okay. And then I can go to here. And let me repeat from 4 to plot. Okay, so I repeat the counting, etc. And I go to console. Now you see that the graph is much smoother. Any question? No problems? This is great. Okay, now I think actually here there is something that it's not good in the graph. There is a mistake here. And what is the mistake? The mistake is that the area below the probability density curve should be 1. Because you know that probability is varying from 0 and 1. The integral of probability density then should be 1, because I mean, probability cannot be greater than 1. If you look at the area below this graph, it's not 1. It's something like 100 times 4. So it's 400. So where is the mistake here? The mistake is here. If you look at the plot instruction in the console, I still used the number 1000, not 1 million. So what I have to do is to repeat the plot. And here I have to put 1 million. But instead of repeating the whole cycle, let me get only the plot to be repeated in the history to console. And let me put here 3 more zeros. Now you see that the graph is correct. The area is 1 below the curve. And how can we check that the area is 1? We can take a summation, we can make an integral, and the integral is nothing else than a summation. So let me change this plot and put here a function. Instead of plotting against PR3, instead of plotting PR2 divided by 1 million divided by 0.1, let's plot the cumulative sum of it. The function cumulative sum can be written in this way. This cumulative sum substitute the vector with a cumulative sum of each element. So you see that now there is still something wrong here, because it is 10, which I made a mistake, and let me understand why. First of all, let me get the previous plot here. This is indeed correct. So let's now make, let me just look at this, because it goes to 10, which is something that it's not correct. So just 1 second. Should go to 1. Let me get the previous plot, and I want to make a check, because it's 0.2 times 4, which is, yes, this is indeed 1. So it's a trivial mistake that I'm doing. And let me see now the cumulative sum of let me see, cumulative sum of PR2. Let me make use a double parenthesis to make sure that 1 million, I think it's indeed 1 million, the length, and then I need to check if everything is correct. Let's see, I forgot a parenthesis, I'm sorry. Okay. And this is something, just 1 second, I need to make some check, just 1 second, because I need to make a sum of PR2 and check that it's 1 million, yes. So first of all, if I look at the minimum of PR2, it's PR1, sorry. It's out of the range. So when you basically I'm missing some observations, but this is not a problem actually. And also the max of PR1, it's probably it's larger than 4, but this is not a problem. it's larger than 4. So what I'm getting is I'm not covering the whole range with this plot, but in any case, this is anyway fine. And let me check the length of PR1 because I want to make sure that there are no mistakes. It's indeed 1 million, correct. And now if I make a sum of PR2, this is 1 million, which is fine. And then the length of the interval is 0.1. Let me see PR3. Yes, it's 0.1. So let me clear the console and let me make the final check, which is the cumulative sum. Okay, so it's PR2. And let me see. It goes to 10. So 1 second. Okay. And let me put here again 10. So there is something that I am missing, and which is just related to the cumulative sum, and I think it is a trivial mistake, but anyway, let's do one thing, and then because I want to move forward with the lectures, and then in the break I will resolve the problem. Let me just stop here with the plot of the probability density. This looks correct because if you look at the area below this curve, it is something that goes, it's given by the product of from -2 to 2, I have 4 times the average, let's say, ordinate is about 0.2. So 0.2 times 4, it's indeed something that is close to 1. So this is correct. And then I am making a mistake in the computation of the cumulative probability density. In computing the cumulative probability density, I should just take a sum. Yeah, I remember why. Sorry, I got it. So in computing the cumulative probability density, I need to multiply it times delta x, because it's an integral. I was forgetting the delta x in the integral. So this is divided by 1 million, okay, times 0.1. And this is now summing up to 1. Very good. Let me make the plot now. I'm sorry, I forgot the delta x. Be patient with me. I'm getting old. So here I need to, this is okay. And then I need to multiply times 0.1. And sorry, I forgot the cum sum. Cum sum. This is the correct instruction. Okay, good. This is the cumulative probability density, which goes in the range -4 to 4, goes to 0 up to 1. Now we got it correctly.
Excuse me, can I ask a question?
Yes, please.
In the function cum sum,
Yeah.
PR2 over 1 billion, why do we divide by 0.1 if we're gonna multiply by it?
Yeah, of course you may avoid it because I am doing 2 operations that cancel each other. But when I compute the probability density, let's look at this one. Sorry. This is the graph of the probability density. Here, no, this is not the correct one. Just 1 second. The graph of the probability density, it's the previous one that we got. It's this one. Okay, very good. Here you have to divide by 0.1 because PR2 divided by 1 million is the relative, it's the frequency. And then the frequency has to be divided by the delta x. So let me get back the formula because I have the formula here. Just 1 second. I need to just, here it is. So you see that you have the frequency at the numerator, and at the denominator, you have the length of the interval. And just keep in mind that in this formula that you see on the screen, the length of the interval was called 2 delta x. In our case is 0.1. Okay, so basically it's clear to you?
Yes, yes, yes. Very clear.
Okay, perfect. And then when I compute the cumulative sum, and then this is the plot of the cumulative sum, of course, I may have, I need, this is an integral. The cumulative sum is an integral, and you have to multiply times delta x. So of course, I would get the same result if I cancel the two. But I prefer to be clearer. Okay, good. Now, I think we can close here with some key messages. What did you learn today? First, let's focus on R. You have learned how to make cycles, and you have learned several functions, from min to max to cum sum to length, and you have also learned how to put conditions on a vector, like with the square parentheses. So for instance, if I make PR1, this is a vector with 1 million elements, okay? And if you type return, you get on the screen, you see what's written there. It's in principle, it should write 1 million elements, okay? But now let me clear it. If you want to put a condition on the vector, like print on the screen, the instances PR1 with the condition PR1 greater than 4, then you are printing only the numbers that are greater than 4. And then in our case, I wanted to compute the length of it. So let me make it here as an example. Okay, and this is the condition that we learned how to put a condition and how to put a second condition, and PR1 lower than 450. But here I have to put the square parentheses here, okay? And so you learned how to put conditions on vectors. We learned a lot of things, okay? And we learned how to manage the history, how to bring back the instructions in RStudio from the history to the console. On the theoretical ground, I hope that I contributed to make you understanding what is a probability density and what is a cumulative probability. So I think that by doing an exercise, it should help you to better understand, okay? At this stage, I would propose to close RStudio and to go back to our web pages with the lectures. Good. Now, here we are, okay? Look that this figure that you see on the screen is nothing else than the density that I have computed with R, you see? And this is computed by throwing 2 dices, but it's the same thing. While I computed it by using random numbers that were generated by the PC, okay? Very good. Now let's go to the last thing that we discussed, which is, let me increase the font, and the wind forces against the ships. This is what we last discussed. Remember what is the ballast and what is the meaning when we say that a ship is in ballast. And just 1 second, because I have a call from a colleague and I rejected the call. Okay, so a ship is said to be in ballast when it is carrying ballast only, and the ballast is the stabilizing weight. Ballast in ships is often obtained by loading water. Keep in mind that when a ship is in ballast, it's more exposed to side winds because the windage area it's larger, okay, because the ship goes up out of water while keeping stable, and so the exposed area to the wind is larger. Okay. Now let's go to our relationship, and I told you that it's better if you if you learn this by memory. And remember, we said that this CW is a wind force coefficient. We said that the quantity between parentheses is the exposed area of the ship to the perpendicular component of the wind. So this is why we multiply by sin square phi and cos square phi, because this allows us to project the area perpendicularly to the wind direction. And then remember that this quantity here is wind pressure. We didn't say this last time because I ran out of time, but this, what is selected here, it's the product of specific gravity of air times the velocity of the wind squared divided by 2g. This is wind pressure, okay? And by assuming that the wind is acting perpendicularly to the exposed area, okay? This is wind pressure. Okay, now we concluded by saying that CW depends on the shape of the wind, and we suggested an increasing coefficient 1.3 for wind crosswise to the ship, while for the wind against the bow we can get 0.9, and for wind against the stern we can get 0.8. Very good. Now we need to apply this relationship. I go back a little bit. We need an estimate of AW and BW. And these are the windage areas of the ship. They are a ship behavior. They may be given by the producer, or they may be given by the authority that is in a way authorizing the ship to circulate, okay? And in case you want to get some orders of magnitude, I scroll down the page because here there are some indications, and I'm scrolling down. For computing AW and BW in absence of known values, okay, and these known values can be given again by the producer or by the authority licensing the ship to circulation. But if you don't have known values, you can apply the following relationships. So AW is given by this product. You don't need to learn this by memory. And let's just understand what are the variables there. So first of all, AW is the side area, the side windage area. And it's given by the product of the length between perpendiculars, which we already defined. I will remind you in a minute what is, which multiplies the length between perpendicular, multiplies the sum of G plus Z. G is ship's freeboard. I will remind you what is, and Z is the mean height of the longitudinal area, okay? And it's clear what is the meaning of this relationship. You multiply the longitudinal size of the ship, an estimate of the longitudinal size, you multiply it by the sum of the freeboard and mean height of longitudinal area. For the transverse area BW, you multiply the beam. Again, I will recall you in a moment what is the beam, by the sum of, again, G, freeboard, plus Y, which is the mean height of the transverse area. And I think we need to recall back what are these lengths between perpendicular, beam, freeboard. So let me go up along the page, or let me do like this. I open another window of the same page, and here I am And this is the figure that I wanted to show you. So basically, here you can see the length between perpendicular, which is, if I well remember, it's OA. Let me just check, because I have a hole in my memory. The length overall, no, length between perpendicular is PP. So particularly, if you see here, this is the length between perpendicular. Look at my mouse. I'm sorry if I didn't, I had an amnesia, I didn't remember it in the first instance. And then the beam is indicated here with the symbol B, and the freeboard is F here. Okay, and you know, you may remember that the transverse area and transverse area is given by the product of the beam plus times what? Times the sum of freeboard plus the height of the exposed area in the transversal direction above the deck. Because here freeboard is measured with respect to the deck, but you may have an area of the ship above the deck that is exposed. And therefore you understand the physical basis of the two relationships that I proposed to you here. So here with different symbols, I'm sorry for that, but G is the freeboard and Z and Y are these representative dimensions of the ship superstructure above deck. So you can understand the physical basis of this indication. And I use different symbols because I took from two different sources these notes. And in particular, this one is taken by the Ports Designer Handbook. Now, of course, the maximum wind force in the equation, in the above equation, I go up to show it to you. You can get here a max of this force depending on the value of phi. Okay, so if you look at a given direction like the longitudinal direction or the transversal direction, you can find a phi value that maximizes the forces. And if you go down, you get when you have phi which is equal to 90 degrees, namely the wind blows perpendicular to the ship center line and blows against the side of the ship. This is the max wind force, because if you have the ship acting against the bow or against the stern, it is the transversal exposed area of the ship is lower than the longitudinal exposed area. So in order to get the max of the wind force, you have to put you have to take the wind that is acting perpendicularly to the longitudinal area, so phi is equal to 90, and you get this expression for the max, which is CW, and CW will be equal to 1.3 times AW, which is the longitudinal exposed area of the ship, times P. What is P? P is the product of these two factors, which is wind pressure. Okay, and I'm providing in a figure just below a schematic representation of the relationship between wind pressure and the wind velocity. Okay, and this formula, this representation is useful because it gives you an order of magnitude. This is the representation I am referring to. So here you have the wind pressure on the horizontal axis, which is expressed in kilonewton per square meter. And in the vertical axis, you have the wind speed measured at 10 meters above flat terrain, with an average duration of the gust of 10 minutes. And it's actually, sorry, with a wind duration of 10 minutes. You see two curves. Why two curves? Because the lower one, which gives higher pressure for the same wind velocity, the lower curve, which gives higher pressure, refers to a gust factor of 1.2, which is the safety condition that we should adopt. So basically, in this figure, the last thing to say is that we make reference to this wind speed, 10 minutes average duration and 10 meters above flat terrain, because we want to get a correspondence with the wind classification, which is reported in the right vertical axis. And you may remember that this classification refers precisely to the wind speed that has a duration of 10 minutes and has a and is measured about it's measured at 10 meters above flat terrain. And this classification we already considered here. Let me go to the other page, and it's here. It's the Beaufort wind classification scale. Just 1 second. It's here. Okay. So basically, the Beaufort wind force scale is reported in this figure on the right axis, and you can see here the progress of the wind pressure. With we should make reference to the lower curve, which is the higher pressure given by a gust factor of 1.2. Okay, this is useful in order to estimate the wind forcing, and of course you have to keep into account that if when you have a wind force acting over a ship, what happens? First of all, the ship may rotate. If the center of gravity of the exposed area to wind is not coincident with the rotation axis of the ship, which is physical behavior of the ship, and we will discuss how this rotation axis is identified. So when the center of gravity of the exposed area to wind is not coincident, it's not superimposed to the rotation axis, you get, after the action of wind, you get a drift of the ship, which means a translation. Sorry, a translation, not a translation, a translation of the ship, which is actually, it's called in English drift. And then you get a rotation. Now, if the ship is moored, the resulting load is distributed, it's transferred to the berths. And this is what is our concern. This is our task, to estimate how the load by the wind is transferred to the berths, because depending on this load, we have to size to design the berths. And in particular, we have to design the moorings and the whole berth structure. So we are interested in the distributed loading on the whole berth structure, and we are interested in the single loads of each mooring point. Now we got how to estimate the wind forcing against the ship, and now we have to discuss how this forcing is to be transferred to the berths. Do you have any questions so far? Okay, this is good. Let's now discuss the loads, because we so far discussed the wind force. Now the loads. And of course, we learned that the wind force is given by the product of the considered component of wind pressure by the product of the wind pressure by the area of the ship above water, which is projected over the longitudinal or transversal direction, okay, according to the equations that we discussed. Now, keep in mind that this exposed area, and now we come to the discussion of the ship conditions, depends on the overall ship geometry, but also depends on the loading of the ship, including the ballast load. And to give an order of magnitude, I am describing on this web page what is reported in the Ports Designer Handbook by Torresen. And he makes reference to a modern cargo ship with a tonnage of about 30,000 tons, fully loaded, and in such a condition, such a ship, a cargo ship, a modern cargo ship with a total displacement of 30,000 tons, if it is fully loaded, has a wind area of about, and this is an order of magnitude, 15 square meters per meters of ship length, okay, in the longitudinal direction. So you take the length between perpendiculars, and if you take the total longitudinal area exposed to wind of the ship and divide it by the length between perpendicular, you get something like 15 square meters per meter of linear longitudinal length. The same ship, if it is in ballast, may have an exposed area which is 30% higher, and it can reach about 20 square meter per linear per meter of linear longitudinal direction. And if you have large passenger ships, they may have a wind area in the longitudinal direction of even more than 35 square meters per linear meter of longitudinal direction. So you understand that two things. First, a passenger ship may have a considerable exposed area, and second thing, it depends very much if the ship is in ballast conditions or not. So of course, the most dangerous situation is given by the ship that is unloaded. It's only in ballast, it's in ballast only. And in this case, you get, of course, the higher exposed area. Now, we already said that if the wind blows at an angle to the ship, which is the usual situation, there will be two components. So the transverse and the longitudinal load plus a possible rotational moment. And to estimate the distributed load caused by wind along the direction along the berth, it is very simple. So if you get a given direction on the berth, and for instance, the longitudinal direction of the berth, and you call it with X, and you want to estimate the distributed load over this longitudinal direction, what you have to do is just to take the component along that direction of the wind load over the ship and divide it by the dimension LQ, which is the dimension of the berth along the considered direction. So if you have a berth that is 50 meters long, and you get a longitudinal component of the wind against the ship, which is equal to, let's say, 50, whatever the measure unit is, you divide the total component of the load, of the wind load, by the length of the berth, and you get the distributed load. What is the meaning of this distributed load? You should use it to estimate, to design the berth structure. And then, of course, the load is not uniformly distributed. It is concentrated over the mooring points. So computing the individual load per each mooring point, it's another story. We will see how to resolve it. It depends on the position of the mooring points, of course. But the distributed load is just given by the total divided by the size of the berth. And I think that this is very simple. I mean, you just have to divide the total by the size. And of course, when we will get to the computation of the mooring loads, as I said, it depends on their position. And we will make an exercise about it, not today, okay? Now, what if you have a berth where ships can approach it on both sides? How to estimate then the action of two contemporary wind loads given by two ships approaching the berths on different sides? Here is the rule of thumb. The total wind load acting on the pier should be approximately the wind load on the largest ship plus 50% of the wind load on the ship on the other side. So you have a reduction coefficient which basically lowers the wind load on the other side of the pier, which is 50%. And here, and then we make the break after this discussion, there is an interesting figure which we already used in order to identify the angle phi that we used in the computation of the wind forcing. Remember, we said just a few minutes ago that when phi is 90 degrees, it means that you have the wind acting perpendicularly to the longitudinal direction of the ship. And this is precisely what you see here. But what is also interesting is to look at the terminology of the mooring lines. So this is a typical configuration of mooring lines. Of course, this is not dictated by any law in force. It's just best practice in order to make sure that the ship is safely moored. So you have the headline, number one, to keep the forward part of the ship against the dock. And then you have number two, the forward breast line, keep close to the pier. And it's also similar to, the function is similar to number five, the aft breast line, keep close to the pier again. And then you have 3 and 4, they are called 3 forward spring, and 4 is the aft spring. These two mooring lines prevent the ship from moving back and forth. Okay, it's clear, 3 and 4, they prevent the ship moving forward and backward. And then we already said about 5, and number 6 is the same function as number 1. It's called the stern line, prevents forward movement. I suggest that you, when you get an opportunity, go in a port and look how are the mooring lines displaced. It's extremely interesting. Keep in mind that these mooring lines do not run horizontally. Usually they run at an angle with respect to the horizontal direction. I would stop here for a 15 minutes break. I would like to kindly ask you if you have any question, and please don't be shy. It's important that you resolve your doubts. Okay, so let's take a 15 minutes break and I keep the recording running, so you will have to just skip it if you look back at the videos. Let me check on the chat. Yeah, no questions. Okay, see you in 15 minutes. Thanks. Here I am, students. Now, I just would like to remind you that we will close in about 1 hour from now. I would say 12:25, something like that. And then we will recover the half hour left in a subsequent opportunity. I just wanted to ask you if you have any lecture in the afternoon on Tuesday, just to know if we can, if I can take, for instance, next Tuesday half hour more. Would you have any problem if maybe when there is an exercise to make, I take half hour more? Usually I should close this lecture, if I was on time, I would close the lecture at 1. Because it would be, and then it would become 1:30. Do we have any problem if next Tuesday I close at 1:30? I'm looking on the chat. It looks like you don't have any problem. Okay, I just, I think it may be next Tuesday. I would like to when we make the exercise, which is a bit complicated. Okay. I see that there is Farid said that it's okay. I would like to make sure that we recover the half hour when we make the exercise, because otherwise it becomes too long. You know, already 4 hours, 4 consecutive hours, it's quite a long time. Okay, now let me move forward, and here I am with the screen, and we now have to talk about the rotation of ships. And so, as I already mentioned to you, when after wind forcing, we may get drift for the exposed ship, and we also may get a rotational moment. It is important to estimate both components, because when we compute the forcing on the mooring points, the rotational moment, it's also important, as you may understand by intuition. And so we need to understand the dynamics of the rotation of a ship. And in order to understand it, we need to define the pivot point, which is the point around which the ship appears to be turning for an observer standing on board of the ship. It's basically the pivot point is the point where the vertical axis of rotation passes through. So what does this mean? If you get a rotation of a vessel because you get a moment that is acting on the vessel, and the moment is originated, for instance, by a wind force that is acting on the ship, and under some conditions, the wind force may generate a rotation. You can understand why. When the conditions when a rotation is originated is when the wind force that is acting, for instance, on the longitudinal area of the ship is centered on a point that is not centered, is not aligned with the rotation axis of the ship. So if you get the wind force that is, for instance, centered on the stern, on the part of the ship that is close to the stern, it's your intuition that the ship tends to rotate. And why? Because the wind force is eccentric, is not passing through the rotation axis. The rotation axis of the ship, it's a vertical axis that passes through the so-called pivot point. So once you define the pivot point, which is the point around which the ship rotates, if you draw a vertical axis, a vertical a vertical line through the pivot point, you get the vertical axis. And what does the definition say? The pivot point, it is the point around which the ship appears to be turning for an observer that is standing on board. So basically, if you stand on board of a rotating ship, you can identify the point where the ship for this observer is rotating around. And this is the pivot point. And for a resting vessel, the pivot point, it's coincident with the center of gravity of the underwater body of the ship. This is something that you can understand because if you look at the ship, what matters for the ship rotation is the ground, the underwater body, which has a center of gravity, and this is, by intuition, you can get that this center of gravity of the underwater body is precisely coincident with the pivot point, because it's the underwater body of the ship is what keeps the ship stable. It's a kind of constraint to ship movement, of course, and it's the underwater body is what is conditioning the movement of the ship in terms of drift, in terms of rotation. This is what is conditioning. If the underwater body is larger, you get more resistance to movement of the ship. If the underwater body is very small, you understand that the ship has a low resistance to movement. So it's what really constrains the movement is the underwater body, and the center of gravity of this underwater body is precisely defining the pivot point. And but this is for a resting vessel. It's important to note that when the vessel moves, the pivot point moves as well. And it's no more coincident with the center of gravity of the underwater body. And in particular, when the vessel moves forward, the position of the pivot point shifts forward. Here it's written. And for typical velocities of vessels that we may experience in the ordinary use of the ship, the pivot point moves forward about 1/4 of the length of the vessel from the forward. And when the vessel moves back astern, the position of the pivot point shifts in the other direction. So 1/4 of the length from the stern. So it's important to notice that, of course, in our case, we focus on resting vessels. We are interested in the rotation for berthed ships, for moored ships. So we are not really interested in what happens to the pivot point when the vessel moves. But keep in mind the definition of the pivot point. This is something that I can ask at the exam. And keep in mind that the pivot point for a resting vessel, it's one thing. The definition is the center of gravity of the underwater body. For a moving vessel is a different thing. And keep in mind that when the vessel moves forward, the pivot point shifts forward, and etc. Okay, and rotation then is originated when the center of gravity of the windage area, which is what basically dictates the wind forcing, the center of gravity of the windage area does not coincide with the pivot point. So it happens that the wind forcing is acting on the center of gravity of the windage area. And if this is not coincident with the pivot point, you get an eccentricity of the forcing with respect to the rotational axis, and therefore you get rotation. And Of course, when the vessel is berthing, you know, the velocity of the vessel is almost coincident, is close to zero, and therefore the pivot point is almost coincident with the center of gravity of the underwater body. But so we can locate in a way what is the location of the pivot point that is interesting for us. And so this is extremely important, because by knowing the position of the pivot point and knowing the position of the center of gravity of the wind edge area, we can compute the rotational moment. And we will see in a practical exercise how this can be carried out. Okay, now for the wind forcing, we are done. We will now discuss again later about rotation, about computation of the mooring forces, but after we discussed a second source of forcing on the berth, which is given by wave forces. Before I move forward, please let me know if you have any question. I would like to give you an opportunity to ask questions, if any. Okay, now the next chapter is wave forces, and this is another important forcing for designing piers, berths, for designing also mooring points. We discussed wind forcing, and wave forcing is generating a comparable forcing. Again, it's forcing originated by waves on moored ships, which is transferred to the mooring points and therefore the berths through the body of the ship. We will also analyze, discuss forcing originated by tides, but by far, the forcing originated by tides is less important than the forcing originated by wind and by waves. I think you already discussed with Professor Archetti wave forcing, and I think you discussed it when talking about the design of coastal defenses, the design of breakwaters, and you know that you need to refer to extreme wave conditions, of course. And extreme wave conditions, because even if the port is basically a sheltered area, it's an area where wind forcing is attenuated, because we have protections, we have structures that are mitigating the action of waves, but still it may happen that you get important wave forcings also inside the harbors, and therefore you have to refer to extreme conditions and apply statistical methods for estimating what is the expected wave forcing. And in order to estimate it, as I said, you know that you have to apply statistics, and therefore you know that you need observations for possibly a long period, because we are describing a random forcing, and this random forcing, of course, it's to be understood, to be deciphered by looking at observations. And in some cases, it may happen that you don't have observations available. And in some cases, you may need to install monitoring systems in order to be able to collect at least a significant number of observations. And what you need to observe is wind behaviors, so the extreme wave height, the extreme wave amplitude, and the extreme wave wavelength. And you also need to know the dominant wave direction. keep in mind that if you install new monitoring systems, before getting a reliable representation, a reliable statistical representation of wave forcing, you need to observe, you need to collect observations for at least 1 year. This is one indication, but in general, 1 year, because you need to cover the seasonal period. You need to get observations in all seasons. But actually, when we are talking about extreme waves, we are talking of something that may happen once, on average, once every 50 years, once every 30 years, once every 100 years. And therefore, you can easily understand that if you have only 1 year of observations, it's problematic to define the behavior of something that it's unlikely to occur during a short observation period. So you just have to be aware that when you want to estimate extreme natural phenomena of whatever nature, maybe waves, maybe rainfall, maybe floods, and you refer to something that happens on average every, let's say, X years, X may be 30, 50, 100. Rigorously speaking, you need to collect observations for a period that should be as long as the period X, which means if I am designing a structure for a lifetime, an expected lifetime of the structure of 50 years, then I should refer to extreme conditions that may happen on average every 50 years at least. So I start from the design lifetime of the structures, which for a birth is typically 50 years. Then I should design the birth against something that may occur once during the lifetime. And therefore, in principle, rigorously speaking, I would need observations for a period that is as long as the design life. So when I say 1 year of observation, it's clear that this is the very minimum that you may rely on. So let's say that in general, statistics allows us to compensate for the lack of data. But we have also to be fully aware that statistics means uncertainty. The shorter the data set that we have, the larger the uncertainty. And therefore, you have to be fully aware of what is the risk of designing something that on the basis of very limited observations, and how to compensate, how to reduce this risk by using safety factors. So the shorter the observation period and the more appropriate could be to adopt a larger safety factor. Now, first of all, let's focus on what happens to waves, how waves move. You already know this because you studied the dynamics of waves with Professor Archetti. And so waves are produced, are originating a transfer of energy. It's not a transfer of mass, it's a transfer of energy. But after breaking, if the waves break, the transfer of energy is transformed in a transfer of mass. So after breaking, indeed, you have water that is moving. And before breaking, it's just a transfer of energy. It's water that goes up and down, but doesn't move forward significantly, forward or backward. And the first thing is that you should make sure that the port is deep enough to avoid breaking. Why is that? Because clearly you understand that if you get wave breaking into the area of the port, then you get into a situation that is more dangerous in terms of forcing that is originated by the waves. And so we should make sure that inside the port we don't have breaking waves. And in order to avoid, breaking, that you should make sure that you have sea depth that is large enough, because breaking is originated by the interaction of waves with the sea bottom. And there is a useful formula, empirical formula, that may tell you what is the sea depth that we should, the minimum sea depth that we should adopt to avoid the wave breaking. And the formula is selected is here. It's dB, which is the sea depth at the breaking, is more or less equivalent to 1.28 HB, where HB is the individual wave height at the breaking. So once that you estimated the expected wave height, extreme wave height, we should make sure that the water depth in the Arbor, in the port, is larger than dB. In this way, we avoid wave breaking. Okay, and let's say that, as I mentioned, when there is the need to, when we estimate the wave forcing, we can adopt a relatively reduced wave height as design wave with respect to the maximum height that you would estimate in OpenSea. And this is because structures in the berth structures are usually resistant to the high loads originated by wind forces and mooring, and therefore they are not likely exposed to destruction by wave forcing. And in this way, given that we are designing berth structure with respect to two contemporary forcing, and given that also harbors and ports usually experience a reduced wave height with respect to the open sea, we can usually adopt a reduced wave height. Now, in particular, let's keep in mind that we need to refer to a return period, and we will need to define what is when we refer to wave height estimation. Before moving forward, let me make some highlights on what are the behaviors of the harbors and ports that have any influence on the characteristic of waves. Why it is important to highlight this? Because this points out what is the information that I require to support the design. First of all, bathymetry of the sea bottom, of course, in the vicinity of the berth structure. And also we have to take into account the reflection of waves that here there is a spelling error, I'm sorry, and I need to correct it. Let me take a note. So, sorry, I take a note because otherwise I forget. And it's second bullet point. Second bullet point. Behaviors, okay. And it's reflection of waves by the near shore structure or slopes. Let's say that we have to take into account once we design the layout of the harbor, we have to take into account the reflection, and you know what is the reflection, and also refraction. We have to take into account the refraction of waves. We have to take into account wave shoaling. These are all phenomena that you know, and therefore I'm not redefining them. And of course, we have to take into account the wave regime, which we monitor through observations. And observations can be collected through several monitoring means, which we discussed in coastal engineering. It may be direct observations through staffs. It may be also observations collected through a camera. Here you see a box that is something that I placed there here, not because it's interesting for ports. I think this is something that is really interesting for as a general knowledge, and it is related to what is a monster wave or rogue wave. Sometimes it happens that some ships in open sea disappear, and we don't understand what happened. So it's important that we know that it may happen in open oceans, not in sheltered areas. So it doesn't happen in ports or harbors. So for this reason, I say that this is placed inside a box, because it's not directly relevant to the design of ports. But it is something that I think it's interesting that you know. Sometimes in the open ocean, for a series of non-linear effects that may superimpose, sometimes it may happen that a very large wave is generated. As I said, for the superimposition of effects that are non-linear. What does it mean, non-linearity? It means that the superimposition of effects is not just given by the sum of the individual effects, but rather by a multiplication. So I mean, if you have two waves that are crossing each other, you know that in the linear theory, in order to get the result of the superimposition of two waves, you may take the sum of the effect of the individual waves. But if the process is non-linear, then the superimposition may be a multiplicative process, not a summing process. So the result is not just the result of a sum, but can be the result of a multiplication, or can be the result of a power law, which means exponential. And therefore, these nonlinear processes, the superimposition of several nonlinear processes, may give rise to something that is extremely relevant. It is related to, you know, the story of the butterfly that flies in Japan and originates a hurricane in the United States. This is precisely another example of nonlinearity. And these nonlinearities may origin in the open ocean, these monster waves. And there is also a Wikipedia page that it's dedicated to it, which is interesting. If you just open it, there are some interesting pictures. And also there is a more detailed explanation. And also you see here a figure where close to a port, there is a warning signal. Of course, if you refer to a port, a sheltered area, these waves may be dangerous if the port is exposed to directly exposed to waves that may come from the open sea. Usually this is not the case for important ports. Important ports are protected, but it may happen sometimes, especially for touristic harbors. It may happen that they are not much protected, and therefore this is something that may be relevant also for the design of berths, but usually they are not. And also keep in mind that these rogue waves usually happen in the ocean. It's unlikely that they happen in a small sea like the Adriatic Sea or the Mediterranean Sea. But I think that this yellow box, which is not something that I may ask at the exam, it's a useful information for you. Okay, and now let's focus on the design wave. I think that you already had some information by Professor Archetti about extreme value theory, how to estimate extreme wave behaviors, extreme wave heights, extreme wave length, etc. I assume that you already have this information, how to estimate, for instance, a Gamble distribution to get an estimate of extreme wave height. So I'm not focusing on that. I just would like to make some remarks and some recap. And an important recap is precisely the definition of the return period. And this is something that I may ask at the exam, and because I want to make sure that you have it clear. The return period, the concept of return period is something that is extremely relevant for you. So you don't have to have any doubt on how it's defined. So what is the return period? Is the average time lapse between two consecutive events with wave height reaching or exceeding a given threshold. So we are talking about wave height here. So again, the return period is defined as the average time lapse, or you may say the average time interval between two consecutive events with wave height reaching or exceeding a given threshold. And don't forget the word average, because this is the usual mistake that we make. So if the return period of a given wave height is 100 years, it doesn't mean that once that you observe that wave height, this will not happen for 100 years. An event with a return period of 100 years may happen twice in a week because it's the average time lapse that is defined as a return period, average, okay? And this is extremely important because actually we don't have any deterministic information that may allow us to be certain about a random event. A random event is random, so we can only speak about its statistics. So average is precisely a statistic. Don't forget to say the average time lapse. Okay, now how do you get the return period for a given structure? The first indication is you should look at the regulations or law in force. For many structures in engineering, the design return period is regulated by existing regulations, law in force, or at least by existing guidelines. And you may assume that the return period of a structure is equivalent to its lifetime, but may be also different. It depends on what? It depends on the consequences that are given, related by a failure of the given structure. So let me give you an example. When we design dams, the design life is expected to be no more than 100 years. But the return period is 500 years. Why? Because a dam failure will have awful consequences. Okay, another counterexample. When we design a sewer system for urban drainage, so it means the drainage of urban roads, etc. The expected lifetime is about 50, 100 years. The design return period usually is much lower, it's about 10 years. Why? Because the consequences of a drainage failure usually are not so bad. unless you have some underground rooms, which may become dangerous if you have a failure of the urban drainage. Unless you are in these conditions, you know, it's not a big problem if a street gets flooded. And so the lifetime is lower than the design lifetime. So the return period is dictated usually by, as I said, law in force, regulations, technical guidelines, and it's estimated on the basis of the consequences of a failure. Okay, and usually I gave you some indications for the berth structures, and it depends on what you are designing. For the structure of the berths, a return period of about 50 years may be an appropriate choice as a rule of thumb. But again, your assessment must be made by looking at the law in force, at the regulations, and by considering eventually, if you still have some flexibility, what are the consequences of a failure. Now, what we need to know in order to make the estimation of the extreme wave height is its probability. And keep in mind that there is a relationship. We can establish a direct relationship between the probability of a wave height and the return period. So in technical terms, we often talk about the return period, but keep in mind that the return period is associated to probability. And in particular, let's recall what is the relationship between probability of not exceedance and return period for the max annual wave height. Let me say something more. Why I refer to max annual wave height? Because a usual method for dealing with this problem, which is estimation of extreme wave height, is to collect the max annual wave height data. And this is a usual way of dealing with, as I said, with this task, because by collecting only the annual max, we limit the requirements, we limit the effort related to monitoring. We don't need a continuous monitoring of wave height, the monitoring that we could obtain with a camera, for instance. We don't need it. We just need to monitor the max of every year. And so it is a classical method to analyze annual max data to get to the estimation. So if you deal with such a monitoring method and you deal with annual max data, you can easily establish a relationship between the return period and probability. And the relationship is shown here. It's just 1 second because I try to, no, I cannot increase, let me see. Now, what do you see on the screen? T is the return period, and P is probability of not exceedance. And it is a very simple relationship. Please remember it. And remember that it only applies to probability of max annual data. Okay, so you have to take in mind that you have to keep it in mind. So if you have data of extreme wave height in the form of annual max, then you estimate the probability of not exceedance of this data, and this is related to the return period by this relationship. Why this relationship is not valid if you have, for instance, the possibility that you have more than one extreme event occurring each year. So instead of having one observation per year, you have 2 or 3, for instance. Why this relationship does not apply anymore? I think you can get it by intuition, because this relationship relates the probability of a number to time. And therefore, the time span with which numbers are observed matters a lot. Because if you have numbers of which you estimate the probability that are observed once in a year, you have only one event per year, and therefore the timing of this number is 1 per year. If you get more numbers in a year, like 3, for instance, you have to take into account that the relationship between probability and time becomes another one. It's different, because probability refers to numbers. And once you want to get a relationship between probability and time, you need to know what is the time span that is passing between each number, each couple of numbers. And for annual max, it's 1 year. Average is 1 year. For other type of data, maybe that they are collected 3 times in a year, the relationship between the time span between observations, it's different. So remember, please, this relationship, and keep in mind that it applies for series of annual max wave height. Any question about this? Now, the other thing that I wanted to discuss with you is the probability that the given wave height is not exceeded in n years. Okay, and this is given by this relationship. So why I am interested in this? Because I am interested in knowing what is the probability with a design life of, let's say, 50 years that I get the given wave height. So the probability that the given wave height is not reached, is not exceeded in n years is given by this relationship here. So I just have to take the relationship between probability and the return period and raise it to the power of the number of years of the expected design life. This is quite interesting because when you make a design, it's important that you take into account the return period, but also the probability that during the expected design life, your wave height is exceeded, and or not exceeded, which is same thing. So from this relationship, you can get an explicit expression for t, and then you can get this graph. What is this graph? I think it is interesting because it gives to you, depending on the return period and the lifetime of the structure. So you have here on the horizontal axis the lifetime of the structure. And then you have here on the vertical axis the return period. And then here you have the probability of exceedance during the lifetime of the structure. And look at this 63% line, the lower one, the lower blue line. What does it tell you? It tells you that for lifetime of 200 years, follow my mouse, you have a 63% probability that an event of with return period of 200 years may occur. So let me state the this consideration in a different form. Let's suppose that you want to estimate a structure with a lifetime of 200 years. Fine. So you may say, I take a return period of 200 years. But then, what is the probability that during your lifetime you get such estimated design wave height? It's 63%, which I think it's extremely relevant. It's an extremely relevant reasoning to make sure that if you take a return period that is the same of the lifetime, you are not mathematically safe, because if you take a return period that is equivalent to the lifetime of the structure, you have a 63% probability during the lifetime to get that event, which is a considerable probability. And this, I think it is something that you didn't know, because it is something that is rarely considered. Like one says, usually one says, okay, if the return period is equivalent to the lifetime, I am quite sure that nothing will happen during the lifetime. No, absolutely. You have 63% probability to get it. And therefore, if you want to reduce and bring it to 10% probability for a lifetime of the structure of 200 years, if you want to reduce it to 10% probability, you have to get a return period of 2000 years. Okay, so what is the matter here? The matter is that if the consequences of the event that may occur with the 63% probability are not much concerning, you may say, but this is fine. I mean, even if I got it, it wouldn't be a problem. It wouldn't be a disaster. So I can tolerate a probability of 63% that it may happen. I can tolerate even something lower than that. But if the consequences are a real disaster, then probably you need to take a much larger return period with respect to the lifetime. And look, if you want a probability of 1%, because you want to be reasonably safe, even for a lifetime of 20 years, you need to get a return period of 2000 years. Now, this is something that you have to consider, because it helps you also to make a proper consideration of the consequences. Let me make an example. The Ponte Morandi in Genoa. The consequences have been awful. 35 people died, if I well remember. Now, this is a case where you can't tolerate a failure. And I'm not sure what happened. I'm not talking with knowledge of that disaster. But I would say that had I to design a new bridge of the same type, I wouldn't tolerate a probability that during the lifetime I get a failure with 63% probability. I need to be more protected. And therefore, these considerations that I made, I think it helps you a lot to make, to understand what safety means. Now, let me be clear. Usually, I mean, it's not a big problem if you get a birth structure that is overloaded by waves. It's not a main problem because the birth structure is already sized for wind forces that usually are very relevant. As I mentioned before, usually you can tolerate the design of the wave forcing with a lifetime for the birth of 50 years, and you take a return period that is comparable to that. You can tolerate a probability of 63% that during the lifetime of the birth you get a similar wave height, but still make sure that you make your proper considerations, and make sure that even if you have some regulations that are imposed by law, you are responsible for making ad hoc proper evaluations that may lead you to increase, to be more protected, even with respect to what is suggested by the guidelines, the technical guidelines, and the law in force. Okay, and so here there are considerations, and you see here there is written, when designing build structure, it is usual practice to adopt a return period of at least 100 years. I just said 50, and keep it as a very rough indication, 50 years, 100 years, depending on the consequences that you expect from a failure. And in fact, here you read, if the impact from failure of the structure is unacceptable, then a return period of no less than 1,000 years should be adopted. If there is risk for human life, be careful, because you may need to increase the design lifetime. Okay, and the design should also take into account if permanence of berthed ships is foreseen for any condition or for limit permanence condition. What does this mean? It may happen that you have a regulation in the port that prescribes that ships are unberthed if an extreme event occurs. And this is, of course, you have to check if tags are available. Tags are the ships that are used to bring the berthed ships out of the port. And you have to make a check also of the logistic, because if the port is designed to berth like 100 ships, is it possible in a limited time? Do you have tag availability that allows you in a limited time to unberth all the ships? But this is possible. I mean, this is a possible solution. If you want to limit the cost and the effort required to build excessively precautionary berth structures, then you may decide that you may rely on an emergency procedure to unberth the ships. A similar solution is adopted for floods. If you cannot protect people, you set up a warning system that tells people to leave their homes if something is likely to happen. And this is clearly a possibility that you have to consider. And if you have instead the need to ensure permanence in any condition, and then once the return period is defined, the significant wave height is computed for each considered wave direction. And I think this is something that you already know, so I'm not giving any more detail. Okay, and as a rule of thumb, I give you some rules of thumb, which are useful to conclude this lecture. I have 5 minutes to go. So, as a rule of thumb, as I said, the Spanish standard, which is something I usually refer to because they are publicly available. And you know that my aim is to refer to, when it's possible, to publicly available information. And indeed, this Spanish standard, let me see if the link is still working. Yes, it's still working. And this Spanish standard is something that is publicly available and you can check. So this is why I'm referring to it. But keep in mind that usually you have local guidelines, local rules that you have to refer to. So this is the suggestion given by the Spanish standard. In other words, the following values should be adopted as significant wave heights for permanence limits of moored ships. Okay, and so for the ships with up to 3,000 tons displacement, and for a pleasure craft, you should get a design wave height of about 40 centimeters. For fishing vessels with length overall less than 30 meters, then we get 60 centimeters. For fishing vessel with the length overall higher than 30 meters, we get 1 meter of significant wave height. And as well, we take 1 meter for other types of ship. And for the ships with displacement greater than 3,000 tons, we get a wave height of 2 meters. These are rules of thumb. And these rules of thumbs are to be applied when permanence is limited. So when we have the opportunity and possibility to unberth the ships in case of an emergency. I would say that I should stop here. Now the next discussion is about computation of wave forces. And it's a similar topic as computation of wind forces. There are some mixed empirical physically based equations, relationships that give to you an estimate of the wave forcing. I wonder whether you have any questions before I shift to the other meeting. And again, I am planning to recover this lecture this half an hour, sorry, next Tuesday. Let me look at the chat. Okay, when I don't see any question, there are several possible options. Either it's too trivial or it's too complicated. Usually when it is, the lecturing is structured according to a proper level of complexity, one should get some questions. No questions may mean that students didn't like it or thought that it was too trivial. But of course, this reasoning applies when you have a wide audience. In your case, the audience is limited, so also there is uncertainty in this reasoning. Anyway, I hope that you are happy with my lecturing. If not, please let me know. And I can also set up, I will see, a survey, an anonymous survey to get to make sure that you appreciate the structure of the teaching and the lecturing. Okay, and thank you very much. So see you next Tuesday, 9:45 as usual.
Thank you. Have a nice day.
Bye-bye.